Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's Semester 1 2023 and this is a revision seminar for Maths 1B. And I've got some requests and I'll start talking about them. I hope it's useful. Okay. That's pretty clear. Okay, so in Maths 1B we talk about second order differential equations, and if you do a future differential equations course, you will do even more different kinds of second order differential equations. But in first year you only look at ones with have constant second order linear differential equations with constant coefficients. In second year, if you do a differential equations course, you will do second order linear differential equations with not constant coefficients. And you will be shown multiple different ways that people over history have attempted to solve such problems. Just heads up in case you do it. And they will begin in the second year course with this when they get to second order differential equations, and they will expect you to remember it. They will go over it from scratch, but faster. So, yeah, I know this because I've only just done the DE's revision seminar for second year. Okay, so a second order differential equation with constant coefficients looks like this. This is just an example of what they might look like. So what they'll look like is that they'll have the function y, which we don't know what it is, and the derivative of y, which we also don't know what it is, and the second derivative of y, which we also don't know what it is, and each of those will be multiplied by constants and added together, and it'll be equal to some function of x or t or whatever the variable actually is. Something like that. So that is what they look like, and just important features that I've pointed out is that these three things appear without any x's multiplied by them. Though it is theoretically possible to have functions involving x in these positions, but they are not called constant coefficients. So in Maths 1B, we're only interested in ones where these numbers are constants. So the linear is referring to the fact that each derivative of y is multiplied by something and then added together. That's what it means to be linear, and the same as linear combination when you do things in algebra. Actually, just a second, I'm going to write that down in a second. I just want to do another example. Sometimes you'll write something, you'll write this as y double dashed instead of just d squared y and dx squared. Might look something like that instead. And it can also not have any x's in it at all, because this bit could be 0 or just a plain number. That's a possibility as well. So these are all various examples of second-order linear differential equations with constant coefficients. And the linear is referring to the fact that y double dashed and y dashed and y up here multiplied by other things and added together and the constant coefficients is referring to the things that the y dashed and double dashed and the y dashed and the y are multiplied by are constants and not functions of x. Technically, a constant does count as a function of x. It just always produces the same answer no matter what x is. That's why I've said not proper functions of x. And so these are the ones that we can deal with. And there are two flavors. One is that if it's equal to 0, it's called homogeneous. And if it's equal to something else, it's not homogeneous. So two kinds. The word homogeneous means all the same. And what is homogeneous about it is the fact that every term involves the function y. But in general, it just means it's equal to 0, and non-homogeneous it's equal to something else, some function of x, or t, or whatever the variable is. How are we feeling about all this? Cool. What's that? Okay. So there you go. So it is possible to have ones that aren't linear, where the y is times by the y dashed, or the y dashed is squared, or some other crap. And it is possible to have ones that don't have constant coefficients, but you haven't been taught how to solve any of those. There you go. Okay. So the way the theory works is this. A second order ODE, ODE stands for ordinary differential equation. I will say it a couple of times, as opposed to PDE, which is a partial differential equation which has partial derivatives in it, which you don't do in Maths 1B. So, but you know what partial derivatives are. You have them in Maths 1B, but you don't do partial differential equations in Maths 1B. Yeah. So, all right, so a differential equation that is second order linear differential equation with constant coefficients. Linear differential equations, whether they have constant coefficients or not, have a neat bit of theory that goes with them, and that bit of theory says two things. And so the two things are a linear differential equation that isn't homogeneous, its solution, so this is fact number one, a linear homogeneous differential equation which will look something like this. It doesn't really matter how many derivatives there are. And there's stuff in these spots. and it's not homogeneous where this isn't 0. The way to find all the solutions to this, or the general solution to this, it's called, is a two-step process. First, find the solutions to the matching homogeneous differential equation. When I say the matching homogeneous differential equation, it'll be exactly the same, but it'll have a 0 in that spot. You have to find all the solutions to that. And when we say solutions to a differential equation, we mean functions for y. Okay, so that's step 1. And then step 2 is find any one particular solution to the original one that before you made it equal to 0. And then add them together. And that will be the general, will be the solutions to the original one. That's the process for linear homogeneous differential equations. That's great, except it requires us to be able to do part 1, which is to find the solution to homogeneous differential equations. And so you have to know how to solve homogeneous differential equations before you can know how to solve non-homogeneous differential equations, because the solution to the homogeneous one comes into the solution to the non-homogeneous one. That is how it goes. Okay, so that's fact number 1. Doing okay? Now we'll do an example. And then fact number 2, which I'm really hoping will fit on this page. A linear homogeneous DE, which looks like this. The reason I'm not putting numbers in these spots is that this actual theorem works regardless of whether there's numbers in that spot or not, whether they're functions of x or numbers. A linear homogeneous DE will always have a two-dimensional solution space from a linear algebra point of view. So what that means is that there will be two functions that are both solutions to this, and all the other answers will be a linear combination of them, some number times the first one plus some number times the other one. So the first thing you need to do is find two different solutions and I will call them y1 and y2, which are the names of functions of x, and then all the solutions are something times y1 plus something times y2. That is fact number 2 about linear homogeneous second order DEs. If they were third order, there'd be 3 solutions and you'd have to combine 3 of them. And if it was fourth order, there would be 4 solutions and you'd have to combine 4 of them. So these 2 facts are the facts that we need to help solve differential equations, that linear differential equations. The hard bit is this part number 1. And the hard bit in this one is part number 2. So the bit where you actually find some solutions to begin with, that's the tricky bit. Once you've got two solutions, then all the rest of them will be linear combinations. Yeah, and I will say the secret last step to all of this is that if you also have information about what y is at certain x's, then after you've done all of this, then you can sub it in to find the actual final answer. So I'll do that too. So I'll just add that. So if also have, you know, y of 0 equals number and y dashed of 0 equals number, or something like that, or y of 0 equals number and y of 10 equals number, or any two bits of information about the function y, then there's only one t in after. Then after you've done this, after you've found all solutions, sub in those conditions. These things are called conditions. Sub in the conditions to find a final solution where it doesn't have unknowns for the a's and b's. But I want to stress really importantly that this step here doesn't happen until you've done all the other stuff. Don't try and sub them in earlier, it doesn't work. And that's a description of the process. The tricky bit is that bit and that bit. Okay, so I'm just going to point out that this fact number 2 is describing how to do part 1 there. So it's part 1, step 1, part 1, and step 1, part 2. These two steps go in here. Okay, so what we need is an example. So just as an example, if someone told you what two solutions to the original, to the homogeneous one was, and one solution to the original was, then you could figure it out. So, for example, if someone said, bear with me just a second. Just a sec. Gonna try and figure something out off screen. No, can't be bothered. Suppose sine of 3x and cos of 3x both solutions to I think I probably got myself into... Suppose these are both solutions to that, and x squared minus 3 on 2x is a solution to this. To that, then all solutions to this are this one solution plus something times that plus something times that. Something like that. So the idea being, if you know two solutions to the homogeneous one, you can create all the solutions to the homogeneous one like this. And if you know one solution to the original, then all the other solutions to the original will be that one plus this. That's how the process works. So technically, to find all of the solutions, you only need 3. 1 to the original and 2 to the homogeneous one, and that will be enough to find all the rest of the solutions. Regardless of whether these are linear constant coefficients or not, this will work. The thing is, for constant coefficients, that's the only time you've been told how to figure out what these actually are. How are we feeling? So this idea is a really important one to hold on to. You just need 3 solutions. 1 to the original, 2 to the homogeneous. And if it is already homogeneous, you only need 2 solutions. Okay. So for constant coefficient, linear second order DEs, the best way to figure out, well, a way to figure out the answer is this. I just want to do one quick example first. Do I? Yes, I do. I just want to point something out, just as an example. The most fundamental and basic kind of second-order constant coefficient linear differential equation, yep, homogeneous as well, is this. That one. And it is linear and homogeneous because I can rearrange it to this. Like that. Okay, well here's something interesting. This is saying that the second derivative of this function is a multiple of the original function. And I know functions, you've seen them before. If you've been, you wouldn't have noticed possibly, but if you've been paying the right kind of attention at the right moment, you may have noticed that there are functions you already know that do that. That function, if I differentiate it, will give me 3e to the 3x because of the chain rule. And if I differentiate it again, I'll have 3 times 3 e to the 3x, which is 9 e to the 3x. And e to the 3x is y, because that's where I started. And so if you have y equals e to the power of something, its second derivative will be a multiple of the original function. What's that? It comes up in Taylor series as well. But this is something that we know to be true. And I'm also going to point something else out. It was a minus 9y. This time the second derivative is still a multiple of y. But if I had e to the power of anything times x, and I differentiated it twice, I'd end up with that thing squared out the front. And so I couldn't get a positive multiple of the original. I couldn't get a negative multiple of the original if it was e to the power of something times x. So just watch this. E to the mu x. Y dash would be mu e to the mu x. And y double dash would be mu squared e to the mu x. Even if mu was a negative number, this would still come out to be a positive. But you do know functions whose second derivative is negative of the original function. Cos and sine do that. When I differentiate that, I get minus 3 times sine of 3x. And then y double dash, the minus will still be there because sine becomes cos, and I'll get this, which is minus 9 of the original function. And it happens with sine as well. And so you've seen them before. Maybe not, maybe you didn't think about it in this way, but they are there. Cos and sine are functions that when you differentiate them twice give you a negative multiple of what you started with. And e to the power of, when you differentiate it twice, you get a positive multiple of what you started with. I think that's pretty cool. And there is one other situation, which is if you start with a linear function, you differentiate it twice, you get 0 times the original function, because you just get 0. A linear function, second derivative is 0. So it is not unexpected that the answer should have e to the power ofs and or coses and sines. That's what I just wanted to point out. That's not unexpected at all as a thing. So what we do is, it turns out, is that we suppose the process is this, okay? If you've got a y double dash plus b y dash plus c y equals 0, then you suppose y is e to the lambda x is a solution. I'm going to skip a bit of the working because this is not important to the process of doing it in an exam. You don't have to show this bit in the middle. I can do it for you if you want, but right now I'm going to skip it. So if you suppose that that is one of the solutions, because you expect that the second derivative possibly being a multiple of the original or possibly involving the thing, you expect this to work, then what will happen is, if this really was a solution, then a times lambda squared plus b times lambda plus c will also have to be 0. How the y double dashed will produce a lambda squared, the y dash will produce a lambda, and the y will not produce a lambda because it's not on the outside here. And this is called the characteristic equation. It is not a coincidence that the same name is used for something with eigenvalues. Not a coincidence because this is an eigenfunction. when you do the process, it gets a multiple of what the original was. And that's what eigenvectors do when you multiply them by matrices. When you do the process, you get a multiple of the original. And so they're eigen things. And so this lambda is an eigenvalue, actually, and that's why it's called a characteristic equation. So there you go. And that's why we use lambda for it as well. Maybe not why. I think these things were invented at separate times and then brought together later. Anyway, and so you solve that and you'll get two solutions. Two numbers for what lambda is. And depending on what those numbers are is how you will respond. And remember, the goal here in this process is to find two different solutions. And when I say different, they're not allowed to be multiples of each other, because they have to be linearly independent. We're making an eigenspace here. So this is a linear algebra thing. So we solve them to find these two numbers, and depending on what those numbers are is how we're going to respond. So if the numbers are two completely different numbers, alpha and beta, I'm going to call them, then your two solutions are e to the alpha x and e to the beta x, or t, or whatever the variable was. And then to create your final list of all the solutions, it'll be some number times a e to the x and some number times e b to the x. Okay. The other thing that could happen is you could get two of the same answer. And in that case, the two solutions are e to the alpha x, and you can't use e to the alpha x again because it has to be different. And those who have trod this path before us have discovered that the other solution is x times e to the alpha x, because they've tried lots of things and this is the answer that worked. And if you get, so this is what happens if you get real solutions. The other possibility is that there are no real solutions for lambda, which would be very annoying to go, oh no, there's no e to the power of lambda x's that are solutions, but all is not lost, because we know that sines and coses also are answers to questions like this as well. And so it turns out that if you get imaginary solutions, then the two real solutions are e to the alpha x times cos of beta x and e to the alpha x times sine of beta x. Which is a very decent magic trick that the complex numbers allow us to do. Technically, we're allowing ourselves to believe that we're actually doing complex functions and there's complex derivatives and all sorts of fun like that, and then we're putting them back together in different ways and finding just the real ones out of the answers we've got. Or you could imagine it as saying, just a second, if I had cos of beta x and sine of beta x, when I differentiate them a couple of times, it will probably come out to be some sort of multiple of what we had before, and so I expect them to be there. So these are the three possibilities that will happen. And then once you've got them, then the general solution, which means all the solutions, is something times one plus something times the other. And you just put the two answers that you've got in these positions and it will be the answer. That's the process for finding constant coefficient second order differential equations, homogeneous constant coefficient second order differential equations as solutions. That's the process. I should do an example with actual numbers in it, right? Okay? So I don't have to actually write down the bit where I suppose it's y is equal to e to the lambda x. It's useful to know that it's there because that explains the presence of the e to the something x in all the answers. That's why it's there. So I will have to tell people that I'm going to do the characteristic. Characteristic. Do you know what? It's okay to just call it char. The characteristic equation is lambda squared minus 3 lambda plus 2 equals 0. And you can solve this by whatever method you think is best. You can use the quadratic formula if you like. You can complete the square. You can attempt to guess two numbers that multiply to give this and add to give this. That's what I'm going to do. So numbers that multiply to give numbers that add to give minus 3 and multiply to give plus 2, they'd have to both be negative. Like to get a negative answer when you add two things together, at least one of the inputs has to be negative. And so to get a positive answer when you multiply them, they have to both be negative. So I need two negative numbers that add to give minus 3. Okay, minus 2 and minus 1. Oh, that really is 2. Cool, awesome. And so it's almost like I set it up that way. Lambda minus 2, lambda minus 1 equals 0. So minus 2 plus minus 1 is minus 3, and minus 2 times minus 1 is 2. And so since these add to give this one and multiply to give this one, I can factorize it like this. And so therefore lambda is 2 or 1. And therefore two solutions are e to the 2x and e to the 1x. And so therefore the general solution, or if you like all solutions, is something times e to the 2x plus something times e to the x. Yay! That's it. That's the end. Bear with me. I'm going to do a little scribbling over here. This one. The characteristic equation is 4 lambda squared minus 4 lambda plus 1 equals 0. Lambda, y double dash becomes a lambda squared, the y dash becomes a lambda, and the y becomes just a 1. Okay, and now I have to solve this. There are many ways to attempt to solve this. You could use the quadratic formula, or you could make it a monic polynomial, divide by that. And then you could attempt to think of two things that add to give minus 1 and multiply to give a quarter. Or you could complete the square. That would work too. Well, they'd have to both be negative. Two things that add to give minus 1 would be minus a half and minus a half. That'd work. Minus a half plus minus a half is minus 1, and minus a half times minus a half is a quarter, and so I get lambda minus a half, lambda minus a half. Which, if you like, is lambda minus a half squared, but the point is I get two of the same solution. And so my two solutions for the original are y equals, are e to the half of x and x e to the half of x, and so therefore the general solution is something times e to the half of x plus something times x e to the half of x. So this bit where you guess things that add to give the middle coefficient and multiply to give the last coefficient doesn't always work, and the quadratic formula is your friend in that case usually. How are we feeling? So it's totally not necessary to write the two solutions line. It just makes me feel better. Just reminding me that that's where it came from. There were two solutions and then I made all the solutions from them. That just makes me feel better to write it. One last example. Let's do one that comes out to be complex. Like that. Characteristic equation is lambda squared minus 6 lambda plus 13 is 0. And I would have to think of two things that add to give minus 6 and multiply to give 13. So it has to be, they both have to be negative. At least one of them has to be negative to give this answer, and therefore they both have to be negative to get a positive answer here. So minus 5 and minus 1 gives me minus 6, and minus 5 times minus 1 is 5. It's not going to work, is it? And I've gotten all the way to the middle and they keep going up. It's not going to get any higher than this. Because if I go further, I'll be minus 2 and 4. That's the highest it's going to get. So it's actually never going to have a real solution. And so that's sad. But I do know that if this was a 9, then this would factorize into lambda minus 3 squared. I'm going to split that 13 into a 9 and a 4, and then this bit is lambda minus 3 squared. And I get to here. And that's good because I knew there weren't any real answers. I can't get a real number squared and get the answer minus 4. That's impossible. But I can get a complex number. When I square root the minus 1, it becomes I. When I square root the 4, it becomes 2. And so lambda is 3 plus or minus 2i. I could have used the quadratic formula. Like I could totally have done this if I wanted, just on the side. I could have done lambda equals minus b plus or minus b squared minus 4ac over 2a. I could have done that, and that would have been 6 plus or minus 4 times 13 would be 52 because of a deck of cards. 36 minus 52. So we'd have to go up 16, I think. And so I get 6 plus or minus 4i over 2, which is 3 plus or minus 2i. So that could have been an alternative way of doing the same thing, which is probably faster, but I just felt like playing around with guessing. I guess the point I want to make is if you've gone to all the effort of trying to guess numbers that multiply and add, then all is not lost. You can use the answer you've got to find the final answer. Yeah. And I could have completed the square, which is essentially what I did here. Anyway, sorry for bringing my love of completing the rectangle into this. I like this process for solving quadratic equations. Anyway, here we are. We have two solutions. Will be e to the 3x cos of 2x and e to the 3x sine of 2x, and therefore the general solution is y equals something e to the 3x cos 2x and something e to the 3x sine 2x. And that's how it works. And they can be much more complicated than that, but the people who write exams try to keep them friendly. I have one last example for you, a really short one. This one. That's the one I had before, where I said the solutions were cos of 3x was one of the solutions and sine of 3x was the other. Theoretically, if you just happen to think of two things that are solutions, you can just show that when you differentiate them, it works, and go, here they are. But I wanted to use this process for it. So the characteristic equation was lambda squared plus 9 equals 0. Lambda squared is minus 9, and so therefore lambda is plus or minus 3i. And just for completeness' sake, that's 0 plus or minus 3i. And so two solutions are e to the 0x cos of 3x and e to the 0x sine of 3x, which, and 0, e to the 0x is e to the power of 0, and anything to the power of 0 is 1. And 1 times cos of 3x is cos of 3x. And so therefore the general solution is y equals something cos of 3x plus something sine of 3x. I just really wanted to show you what happens when you don't get a real part. So if you don't get a real part, the e doesn't appear in the answer, just the causes and the sines. How are we feeling? Sorry? Is that a good thing? Okay. But I will say that if you an alternative working for this would have been just to know in advance that you expect it to be sine and cos, and just make a guess and differentiate them twice and show that it works. I'm not going to write that down. That's not what I'm going to do. But it's not what the people running this course expect you to do, but it's totally correct. If you happen to think of two solutions, then the theory says that all the rest of them will be a linear combination of them. And I could totally tell them, I could totally see them, I have no idea what's in the exam, I'm not hinting, but I could totally see them writing an exam question that says, show that both of these are solutions to this differential equation. What are the rest of the solutions? And then you just differentiate and sub them in, and and it'll work, and then you go, oh yeah, the theory says that all the other ones will be A of this plus B of this. They won't. I wouldn't expect them to say that, but I'd be proud of myself if I wrote that exam question, maybe for second year. Yeah. So that's that bit. We've got many examples of doing this bit here for linear homogeneous DEs with constant coefficients. What that leaves is this bit here. If we have a not homogeneous constant coefficient differential equation, we know how to do this part, we've just done that, and we're definitely going to have to do that part either way. What we need to do is this part now. And that part is found by guessing what you think the answer should be. And actually, even this part was done by guessing what we think the answer should be. We guessed that it should be e to the power of something. And we tried to figure out what the correct value of lambda is to make that work. We've already done a guess what the answer should be part to this. And that is a vibe in differential equations. There are many different methods in the second year differential equations course that go like that. Say, what if the solution looked like this? Then how would I find what the actual numbers or functions that go in here are? And just get used to it. That's just how we do it. And it's actually a really cool mathematical idea to have a little bit of thinking to say, well, I wouldn't, I'd expect that this might be a solution, so I'm just going to hope that it is and see which number is the right number to pick. That's a really cool way of doing things in some areas of maths. It's like, I think this is the answer, and I'll show that it is. Yeah. Okay, so now we're going to do second order constant coefficient. So it has to be linear before you can talk about the constant coefficients. Second order linear constant coefficient non-homogeneous So we know that step one is to find the solution to the matching homogeneous equation. That's step one. It's all the way back here. We know that bit, and we know how to do that bit. So step one to the matching homogeneous differential equation. But if you don't, that's fine and that's great. And then step two is to find a particular solution. Any one of them will do. And when I say the original DE, I mean the one before you made the last bit equal to 0. And then we add those two together and it's the final answer. So that's just reminding you, add to get the general solution to the original. Okay, cool, that's how we do it. And the tricky bit is part two. And the way to do it is that if you've got your DE and it's got numbers in these spots here, AY double dash plus BY dash plus CY equals some function of X, and it's tradition to call it R, possibly for remainder? I don't know. I think it's usually tradition called R because usually you divide by this A so that there's just a Y double dash at the front. And so there's only two coefficients and they call them P and Q, and so the third one is R. That's why. But if it looks like this, then you guess something that looks like R, but simultaneously isn't part of the homogeneous differential equation, and but possibly has different coefficients. So guess Y equals something like R of X, but I'm just going to add a line in here. Something like r of x, there's going to be an extra line in here that I'm going to put in later. Something like r of x, but not in the homogeneous solution, and also with new coefficients. That's what we have to pick. So if the r of x was like x squared, you'd go, cool, 5x squared. That'll be great. Only I wouldn't put 5, it'd be like ax squared because I have to choose a different coefficient. But unfortunately, it's not as simple as that. Something like r of x, and also including all of the derivatives of r of x as well. And all its derivatives. But not in the homogeneous solution with new coefficients. They are the 4 pieces that have to be satisfied to choose the right r of x. So if it has infinitely many different functions that turn up in the derivatives, it's not going to work, but they won't give you one of those in this course. Let me do an example of how this works. So I'll do one of the ones I did earlier. Like that. So this time I don't want the second derivative minus 3 of the first derivative plus 2 of the original function to be equal to x squared, equal to 0. I want it to be equal to x squared. I can't have used as my solution to this anything that's part of the homogeneous solution because I know that when I put the homogeneous functions through here, they give the answer 0 and not x squared. So they can't be the correct answers for this. So I'm going to have to try, so this is my r of x here. So I have to choose something like r of x, but with different coefficients. So I'm going to choose x squared, but with a different coefficient instead. It doesn't matter what the coefficient here was before, even if this was a 7x squared, I would still choose a new number. But I have to include the derivative of this thing, and the derivative of this thing is 2x, and so when I do a new coefficient for 2x, that will be just d. And I have to include the derivative of this, which is just 1, and a new coefficient for 1 is a constant times e. So my thinking was the derivative of x squared is 2x, and then I replace that 2 with a new coefficient. And my thinking here was that the derivative of x is 1, and I replace that with a new coefficient. And you have to keep doing that until you don't get any more new things. So if you had x to the power of minus 1, you wouldn't be able to actually do this thing at all, because the derivative of x to the minus 1 has an x to the minus 2, and that derivative's got an x to the minus 3, and you'd be going forever and ever and ever. So you have to be able to get to the end of the derivatives, because the derivative of just a constant is 0, and well, that doesn't matter. Like, we know that 0 is a solution already. So this is our thinking here that we were thinking about when we did this. And so we will go, cool. We're going to have to differentiate this and sub it in here and see if it works. So that's the next step here. Back here we go differentiate to get y and y dashed and y double dashed, and sub in to find the unknown coefficients. That's the process. That is so badly written. Sub in to find unknown coefficients. This process is called the method of undetermined coefficients, by the way, in case you're wondering. And so I would do y dashed, and that would be 2cx plus d, and then I would do y double dashed, and that would be 2c, and then I would sub them all in. So y double dashed is 2c, we need a y double dashed, minus 3 lots of y dashed is minus 6cx minus 3d, just multiplying this one by minus 3. And 2 lots of y is 2c squared, cx squared plus 2dx plus 2e. And all of this is supposed to come out to be equal to 7x squared. So when I add all three of these things together, I get, as my constant term, 2c minus 3d plus 2e. And as my x term, minus 6c plus 2d x's. And as my x squared term, 2c times x squared. And all of this is supposed to be 7x squared. How are you feeling about the working I did there? I find it easier to write it down the way that I did, like multiplying each of them by the coefficient that's next to it as a separate equation, because then everything's lined up and it's easier for me to add them together. And so I'm going to do the process which is called equating coefficients. The coefficient of x squared on this side is 7, and the coefficient of x squared on this side is 2c, and so therefore the 2c must be equal to 7, and so the c is 7 over 2. So that one was from the x squared coefficient. And from the x coefficient, I've got that minus 6c plus 2d has to be 0, because there's a plane x here, but there isn't one over here. But I know what c is. It's minus 7 over 2. And so what does that give me? Minus 21. So 2d is 21, and so d is 21 over 2. Okay, cool. And then from the constant coefficient, I've got 2c minus 3d plus 2e is supposed to be equal to 0 over here because there is no constant. But I know what c is, it's 7 over 2, and I know what d is, it's 21 over 2. And so I get an answer. Oh wow, it's bad. 7 minus 63 over 2 plus 2e is 0. And so 2e must be 63 over 2 minus 7, which is what is that? So 7 is 14 over 2. 63 minus 14 would be 53 minus 4, which would be 49. Cool. And so the e is 49 over 2 divided by 2 again, which is 49 over 4. I may have made arithmetic mistakes along the way. Sorry if I did. And so my solution is c times x squared was, what was c? 7 over 2. Plus d times x, and d was 21 over 2. And e, which was 49 over 4. And so that is my solution. So it is a solution. If I hadn't have included the x and the dx and the e, I wouldn't have had anything to match up the coefficient of x to, and so it wouldn't have worked. And so therefore, the general solution is this answer that we just had plus the solutions that we had to the other one, which was a e to the 2x and b e to the x. And these are now all the solutions. Because I know that if I run this function through that, well, if I run this function through here, it gives me 7x squared. And if I run these functions through here, they give me 0. And so if I run this entire thing through here, it will give me the 7x squared plus 0. And so will still be 7x squared. That's the reason why it works. How do you feel about what I did there? I'm going to go back and just say something. This line? So this was the particular solution that we just found. And this was the general solution to the homogeneous one. Which we found earlier. If you were given this problem raw, you would have to go and do that homogeneous thing first and then do this. I'm going to do one more. And again, I'm going to pick one of the DEs I've already done. That one. Okay. So I know that the homogeneous solution that we already found earlier, which I should have written down here, sorry, but I'm going to write it down here. Solutions to y double dash plus 9y equals 0, which is the homogeneous equation. Y equals a times sine of times cos of 3x plus b times sine of 3x, which we already had earlier. I'm very much hoping that what I'm about to do is going to work, because I'm still every year finding little nuances in this particular area of Maths 1B that I didn't realise about. So, particular solution to the original. So that was the solutions to the homogeneous, which we did earlier. And the particular solution to the original, I would like to try something that looks like this, but with different coefficients. except I can't use sine of 3x because that's part of the homogeneous, that's one of the homogeneous solutions. And if I run this through the y double dash plus 9y, it will not come out to 5 sine of 3x. It'll come out to 0 because that's what the homogeneous solutions do. So I can't use this. And so what I'm going to have to do So I'm not going to try that because sine of 3x is in the solutions to the homogeneous equation. Instead, I'm going to try x sine of 3x. And this is a generic strategy for for linear constant coefficient DEs, is that if you can't use a solution that you wanted to, times it by x and try that instead. We've already seen that strategy earlier. We saw that strategy just here. We used e to the alpha x, and we can't use it again, so we times it by x. So we're going to use the exact same strategy here. We're not allowed to use sine of 3x, so we'll use x times sine of 3x instead. And so back here when I said, but not in the homogeneous solution, the way to deal with that is to multiply by x. That's what to do to deal with it, not deal with it being in the homogeneous solution. But I also have to include all the derivatives of this. So I would have used back here, I would have used the derivative of the sine of 3x is 3 cos of 3x, and I'd use a different coefficient. I can't use either of those, so I'm going to have to use multiplying them by x. Like that. And so I will try it. Y dashed is, it's gonna get messy. So that's a product rule. So I'll have to keep the cx and differentiate the sine, which would be 3 cos of 3x. And then differentiate the cx, which is c, and keep the sine of 3x. And then I'm going to keep the dx and differentiate the cos, which would be minus sine of 3x times 3, damn it. And differentiate the dx to get a d and keep the cos of 3x. And for the purposes of this, I might just put the causes and the... what do I want to do? Maybe I'll just leave it as it is. Do I want to do that? I might put the causes and the sines together. So I've got 3cx plus d, that many cos of 3x's, and c minus 3dx, that many sine of 3x's. And then when I differentiate it again, keep this, 3cx plus d, and differentiate the cos, minus 3 sine of 3x. And then differentiate this, which is 3c, and keep the cos. And then keep this, c minus 3 dx. Differentiate the sine, which would be 3 cos 3x. And differentiate this, which is minus 3d, and keep the sine. Okay. Wow. Wow. I might do what I did before and put the sines together and the causes together. So I've got a sine here and a sine here, and so I've got minus 9cx from there, and a minus 3d, and another minus 3d, so I've got this. And then with the causes, I've got 3c, and then another 3c, which is 6c minus 9 dx cos 3x. Okay, we are doing okay. We're surviving. And we're going to have to add on to that 9 of y, of the original y. So this up here I've multiplied by 9. And all of this, the total, y double dash plus 9y, comes out to, look, minus 9cx minus 6d, that many sine 3x's, plus 9cx sine 3x's, they cancel, and I get minus 6d sine 3x. And, sorry, minus 6d sine 3x. And when I add this and this, the minus 9dx and the 9dx cancel each other out, and so I get 6c cos 3x. And all of this is supposed to come out to 5 sine of 3x. That's so cool. So I'm going to equate coefficients again, but this time it's going to be the coefficients of sine and cos. So my cos 3x on the left here is a 6c, and on the right here is a 0, and so the c is 0. And the coefficient of sine of 3x on the left here is a minus 6d, and on the right here is supposed to be a 5, so 5 is minus 5, sorry, d is minus 5/6. And so a solution is y equals, now the c went with x sine of 3x back at the beginning here, and c was 0, and the d went with x cos of 3x. So the general solution we keep this thing that we just found, and we add on what we had from the homogeneous equation, which was a cos 3x plus b sine 3x. There we go. I really did not expect to be talking about that for an hour and a half, but I'm hoping it was helpful to go at the speed that I did. I'm going to do one final bit of this question. What if the original question hadn't just been y double dash plus 9y is equal to 5 sine of 3x, but also had the conditions that y of 0 had to be 10 and y dashed of 0 had to be 3? What if? Well, we've already done the bit where we solved this bit without the conditions. And so we know insert working here, the general solution is y equals minus 5/6 of x cos 3x plus a cos of 3x plus b sine of 3x. Okay, we've done all that working. Now, y of 0 is what I get when I put 0 in for x. Like that. And, well, 0 times anything is 0, so there's nothing there. And cos of 0 is 1, and so I get an a. And sine of 0 is 0. And so I get the answer a when I sub in 0 for x into this formula. And this is supposed to be 10. But y of 0 is 10, therefore a is 10. This we know to be true. And so the y is actually minus 5/6 of x cos of 3x plus 10 cos of 3x plus b times sine of 3x. So far I've figured out what one of those missing numbers is. I need to figure out the other one as well. And the other piece of information I have is that y dashed of 0 is 3. So when I do the derivative, look, I already wrote down the derivative of x cos 3x before. It was, no, I'll just do it. Differentiate the minus 5/6 of x and keep the cos of 3x. And then keep the minus 5/6 of x and differentiate the cos of 3x. I'll differentiate this, which will be minus 30 of sine of 3x, and this one will be 3b cos of 3x. So that's the derivative. And y dashed of 0 is supposed to be 3, so let's sub in 0. We'll get minus 5/6 times cos of 0, which is 1, minus 5/6 times 0, times doesn't really matter what any of this stuff is, minus 30 times 0, because sine of 0 is 0, plus 3b times 1, because cos of 0 is 1. And so I get minus 5/6 plus 3b. And this is supposed to be equal to 3, because that's what we told ourselves earlier. So therefore minus 5/6 plus 3b is supposed to be 3, and so 3b is going to be 3 plus 5/6. Wow. I just can't be bothered. And so b is going to be that divided by 3, which will be 1 plus 5/18. Whatever that is. I guess 18/18 would be, 18 plus 5 would be 23/18. And so the solution is y equals minus 5/6 of x cos 3x plus 10 cos of 3x, and then plus 23/18 of sine of 3x. There we go. So that's the bit where you sub in the conditions to figure out what the actual coefficients are. But you can't do that bit until you've got the A and the B, and you get them from the homogeneous solution. So you have to do that bit first. At this point, I think it would be useful for people to ask a question or say something. So that 3 came from differentiating this cos of 3x, and the 3 had to come out because of the chain rule. Derivatives can be difficult to follow from one line to the next because some terms blow out into 2 terms on the next line. So it's very difficult to line things up correctly, especially when you draw symbols at the size that I do. Yeah, good. I'm glad that it's not so much of a drag to do all the differentiation. Really, it's just it is a matter of just focus on one bit at a time and deal with it as you go. Yeah, and I also didn't figure out what this answer was because later on when I subbed in 0, it came out to 0 anyway, so there was no point writing it as minus 5 over 2 or whatever it is, plus 5 over 2. Yeah. And another thing that I'm proud of in the way that I do this is back here when I combine them together, I knew that the sign of the 3x is what I'm going to have to be comparing to the other side, so it was a really good thing to draw those coefficients together and say how many sine of 3x's have I got, which is what I did in the other one. I drew them together and said how many x squareds and how many x's and how many constants have I got. So knowing that I'm comparing to a sine of 3x on the other side meant that I should combine them together, say how many sines and how many coses have I got. So, yeah. And it all just cancelled out, which was just nice. Like, this was great. Very happy with that. And so there you go. You can watch some other videos about the choosing of the shape of the particular form. Sorry, that's how mathematicians write it. Form, not shape. The form of the particular solution. You know, whether it's got a sine and a cos or an x and an x squared. Because I've got a whole lot of what ifs in the other seminars about that. That could be there. Maybe I should do them. So that multiplying by x happens anytime that the thing you've got is part of the homogeneous solution, and if when you multiply it by x it's still part of the homogeneous solution, multiply it by x again. And you have to include all the derivatives of the thing that's there. So if it has infinitely many derivatives, then you can't do this process, and you have to learn something in second year differential equations to do. But if it should at some point come down to having something you've seen before, which is how cos and sine works. So theoretically I should have differentiated this cos again, But if I did that, it comes back to something I've already got, and so I don't have to go any further. Yeah. So that was d on dx of the sine of 3x is 3 cos of 3x. And then if I differentiate this again, I end up back here, and so I don't have to worry about going any further because I've got something I've already seen before. Whereas with the x and the x squared, I kept differentiating until I got down to 0. Yeah. So keep going until you get something that you've seen before, or something that, yeah, and it's fine to just remove anything you've seen before. And it's fine to remove anything that at any moment that appears in the homogeneous solution. Okay. So I guess my recommendation is do this whole derivative thing before you decide whether it's in the homogeneous solution, because you might have to times them all by x for it to work. Okay. Cool. Well, that is that. Oh, that thing?
Yeah. How did you recreate that?
Oh, I did it in Prezi, which is a presentation software.
I found that really cool. I was like, wow.
So there's a slight difference to that I would make to that now. I don't have access to Prezi anymore, which is you're supposed to find the homogeneous one first, and because you have to worry about whether the homogeneous solution is part of the particular solution for the other one. So you can't find the particular solution first and then do the homogeneous, because it might be part of the homogeneous one. You have to avoid the homogeneous solution in the particular one. So, but that, yeah. So that particular thing that I was doing was this, basically. So that was what I was trying to get at, and I don't feel like showing that Prezi right now. But if you have, it was this idea that 2 solutions will produce all the rest by doing the constant coefficients. That's one of the big ideas. Yeah. And today I was very proud of saying the phrase, you only need 3 solutions to find all the rest. One for the particular one for the differential equation you've got, and 2 for the homogeneous equation, and that will be enough to find all the rest. I really like that. That's really useful. Of course, if it was a 3rd order, you'd need 3 for this one. And it would be the same process. Not that they do that. And secretly, for a 1st order one, it also works, which I really love. This is just a secret second bit. I'll do it this way. Y dash plus 3y equals x. This is a 1st order linear constant coefficient non-homogeneous. And you've actually been taught a method for dealing with this. It's called the integrating factor. And that integrating factor, it would be e to the 3x, because you'd integrate this and go e to the power of that answer, and that would be the integrating factor. But watch this. This has a characteristic equation, right? Which would be lambda plus 3 equals 0. Because the double dash would have become a lambda squared, and a single dash becomes a lambda, and so the lambda is minus 3. And so the solutions to the homogeneous ones, so I'll just do solutions to homogeneous. So the solutions to the homogeneous version will be, a solution will be e to the minus 3x, because that's what you do when you get a lambda equals number. You go e to the number x. And since it's only a first order, I only need one solution to get all the others. For a second order, I need two solutions. And so all solutions, the general solution will be y equals something e to the minus 3x. Isn't that cool? And then I would have to find any one solution to this. And so I can say we can find a particular solution. And so my particular solution would be, well, I'll try this thing with a different coefficient, so I'll use bx. But I have to do the derivative of the x, which is 1, and so that would be, and a different coefficient for the 1 would be c, and the derivative of that would be 0, so I can stop. And so y dashed is b, and so I'll sub them in. And so I've got, we had y dashed plus 3y was supposed to be x. And so, just a second, that's what I'm trying to sub into that. So I've got the y dashed is b, and 3y would be 3bx plus 3c, and so y dash plus 3y would be 3bx's and b plus 3c, and that's supposed to be equal to x, and so therefore equate coefficients. The coefficient of x is 3b on this side and 1 on this side, so b is a third. And the constant coefficient is b plus 3c on this one side and 0 on the other, but b is a third. And so therefore 3c is minus a third and 3 is minus a ninth. And so a solution is y is 1/3 x minus a ninth, and so therefore the general solution is y equals 1/3 of x minus a ninth plus a e to the minus 3x. So I could do this by linear constant coefficient methods if I wanted. It's the same process. Yeah. I really should, for completeness' sake, make sure I do this via, probably should do this. Right. You probably should do this. You would go, this is linear, it's linear, and so I would find an integrating factor. And so I'll have the integral of 3 dx is 3x, and so my integrating factor is, do they call it capital I or mu or what in this course? Mu? Is mu, which is e to the power of that. And so I'll multiply everything by e to the power of x. E to the power of 3x, sorry. And then it's carefully set up so that this is the derivative of that, and this is the derivative of that. So that's from the product rule. So if I integrate both sides, I will get e to the 3x times y dashed is the integral of x e to the 3x dx. And then I would have to do that by integration by parts, because it's two things multiplied together. So that would be and if I put the dash at the end, then it'll work. because the x would become a 1 by that point. So x is u, and so there's a u here. A v dashed is e to the 3x, so I'm going to have to integrate it to get v, which would be 1/3 of e to the 3x, minus u dashed is 1, and the v is still 1/3 e to the 3x dx. And so I would get 1/3 of x e to the 3x minus, and the integral of e to the 3x is 1/3 again, so I'll get 1/9 of e to the 3x plus c. And now I have to divide everything by this e to the 3x, and so I'll get y is equal to this divided by e to the 3x, which is 1/3 of x, this divided by e to the 3x, which is minus 1/9, and this divided by e to the 3x, which will be e to the minus 3x, which is the same answer as I got before. Cool, huh? So the power of the integrating factor is it works even when this isn't a constant coefficient dE. So this one is a constant coefficient one, but the integrating factor works even when that 3 is a function of x. That's the difference. Yeah, I just thought I would show that to you because I felt like that was a nice little freebie at the end for something. And I will say that in second year differential equations for engineers, the one with the 0 here, so the homogeneous equation y dashed plus 3y equals 0, they don't even show the working for this. They go directly from here to here, which is kind of interesting. Just point that out. Yeah, so that's just what I wanted to show you, that you can do equations like that via the same methods as doing constant coefficient dEs for second order. It's just that, yeah. And overall, I have to say that integration by parts, I'm always afraid of getting it wrong because there's too many minuses. And so this, I feel more comfortable about getting it right. There you go. Wow. But I just thought I should probably do the actual traditional version, just so you can see how it's done. So this one was divide by e to the 3x. That's how I got to this line here. Well, I spent the whole time talking about second order constant coefficient dEs. Thanks for being here while I did so. I think I might just stop that recording there now.